Welcome to Texas State University Chemistry 2030, Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin. We will continue with Chapter 7, Haloalkanes, Part 3. So in the previous video, we talked about the 4 different things we're going to look at as far as how it reacts to nucleophilic substitution reactions. And those are the effect of the nucleophile, the effect of the substrate or alkyl halide, the effect of the leaving group, and whether or not solvent affects the reaction. Okay. So the first thing we want to talk about is nucleophilicity, and basically that's the kinetic property measured by the rate at which the nucleophile attacks the substrate. So once the nucleophile comes in and displaces it, basically how fast the reaction will go. So if we compare some relative nucleophilicities, we break them down into 3 groups. One are good nucleophiles, meaning the reaction runs fairly quickly. 2, there are moderate nucleophiles where the reaction will run, however, it runs slowly than that of the good nucleophiles. And then there are the poor nucleophiles. These nucleophiles do work, but they react much more slowly than the other 2 groups. One of the things that you can actually compare here is that all the good nucleophiles have negative charges and have lone pairs that they can donate to the system. In the moderates, we now have some negative charges, but we also have negative charges that are delocalized, like acetate ions. We also have neutral species that containing sulfur and nitrogen. In the poor nucleophile section, we now have neutral species that contain oxygen. Okay, so now let's talk about the structure of the actual alkyl halide. So in SN1 reactions or new molecular reactions, it's all governed by the electronic factor, namely the stability of the carbocation, meaning that tertiary carbocations are more stable than secondary carbocations, and primary and methyl carbocations are rarely found. So if you have a primary or secondary alkyl halide, you might be doing an SN1 reaction. Okay? In SN2 reaction, it's governed by steric properties. Basically the relative ease at which it is for the nucleophile to approach the backside of where the leaving group is. That means that the methyl group and primary halides are the more reactive because they have smaller groups behind it, with secondary being intermediate and tertiary being very difficult to have a nucleophile come into the backside of that reaction. So let's look at these again. In the steric factor, we can imagine with just a primary alkyl halide here, we have 2 small hydrogens that are possibly blocking attack by the nucleophile in this direction right here. So that means this nucleophile can come in any of this area here and still form a new sigma bond with that material. However, in the presence of a tertiary alkyl halide, that nucleophile window is very much smaller right here. That nucleophile can only come in this way because the methyl groups with the hydrogens on those carbons are blocking much of the area where those nucleophiles can come in and attack. Therefore, the primary alkyl halide here has a much bigger area for these nucleophiles to come in and attack, where the tertiary ones have a very small, narrow window of attack. Okay, so that being said, our tertiary and secondaries are more likely to go SN1 because they can form stable carbocations. Specifically, tertiary alkyl halides, they form the most stable carbocations of tertiary carbocations, and because of sterics, they never do SN1 reactions. Okay. On the other side of the spectrum for sterics, we have the methyl and the alkyl and the primary alkyl halide. These never do SN1 because the stability of the methyl carbocation and the primary carbocation are very, very low. Therefore, they almost always do SN2 type reactions. The one in the middle, the secondary alkyl halide, is the one that can do either the SN1 or the SN2, depending on some of the factors such as how good the nucleophile is and what solvent you're in. Okay, so now let's talk about leaving groups. The leaving group is the group that must leave, and what we think about there is The stronger the conjugate acid is, the easier it is for that group to leave. So things that have very strong acids like HI, HBr, and HCl, those make really good leaving groups because those are really strong conjugate acids, and therefore those are really weak bases as they leave. That makes them very easy to leave. The next easiest thing to leave would be something neutral, like water. When water leaves as a neutral species, that's a very good leaving group because it leaves no charged species left behind, and it typically is used in, it can be removed from the reaction. Next are delocalized anions like the acetate anion, but then things with hard anions like hydroxide, the basic salts of alcohols and amines are very poor leaving groups because those are very strong bases and therefore they do not like to be eliminated during these reactions. So our relative stability, our relative ability to leave has everything to do with the strength of the conjugate acid. Okay. One of the ones that we can actually play with a little bit is the hydroxide ion. Hydroxide ion by itself is a very strong base, and therefore it's a very poor leaving group. However, if we do the reaction in the presence of a proton donor or an acid, we can get that OH group on the alkyl group to protonate. Once it protonates, we now have that a better leaving group because when it leaves and takes the electrons with it, it leaves as a neutral species. So when you see a substitution with an alcohol to remove that OH group, we're not losing OH negative, we're probably protonating it and losing it as water. Okay, so now let's look into the role the solvent plays. Okay, we have two different types of solvents we're going to deal with in organic chemistry. One is called a protic solvent. This is a solvent that contains an OH, and that hydrogen can hydrogen bond to the substrate or other chemicals in the reaction. Think about anything that has an acidic proton or an acidic pKa is going to act as a protic solvent. So things like water, formic acid, alcohols, and acetic acid. In these solvents, SN1 reactions are favored because it can stabilize the carbocation. Okay? So the second type of solvent we frequently use are what we call aprotic solvents. These are solvents that don't contain a hydrogen bonding group. Okay, so if we look at these solvents here, they tend to be things like acetone, chloroform, ether, carbon, dichloromethane, and another one called dimethyl sulfoxide. This is a very polar compound. None of these have acidic OHs, the hydrogens on the OH, and therefore they actually don't stabilize that carbocation. And so these make the SN2 type reactions more common, specifically with secondary alkyl halides. Okay, to summarize, methyl groups, because they cannot form carbocations, typically go SN2 reactions, okay? They don't form the carbocation, they must use the bimolecular reaction. Primary alkyl halides also do not form very stable carbocations, therefore they almost always go SN2. Let's skip down to our tertiary carbocations. Because of sterics, right there, we do not have SN2 happen. We cannot get the nucleophile into the backside of that, and therefore SN1 is favored. Now, the thing that we have to pay attention to is the secondary alkyl halides. If we're doing a reaction with a secondary alkyl halide, and we have a non-protic solvent or an aprotic solvent and a good nucleophile, the SN2 reaction is favored because a good nucleophile will come in and attack that system. If we are in a protic solvent that can support a carbocation and we have a poor nucleophile, we are going to wait around for it to form the carbocation, and therefore an SN1 reaction is favored. Okay. Now, the last thing I want to talk about is the difference in the stereocenter between the SN2 reaction and the SN1 reaction. Because the SN2 reaction involves that attack of having the nucleophile come in the back and having the leaving group leave out the other side, we get what we call inversion of configuration, meaning that if we started out as an S configuration for our substrate, it is going to invert to become the opposite stereo center. Okay. In the case of SN1, because we go from our trigonal planar optically active material into that trigonal planar intermediate with the carbocation, we can have that nucleophile attack either side, and therefore we get 50-50 attack on either side, and therefore we get one half of it, one isomer, half of the other, or we get what's called racemization, scrambling of that stereo center to give a 50-50 mix of the two possible ones. Okay, all right, so let's summarize this one more time. Okay, so an SN2 reaction happens in one step. It has one hump on its energy diagram, and it's bimolecular. That means that both the concentration of the nucleophile and the alkyl halide are in the rate constant. Because we don't form a carbocation, we do not have carbocation rearrangements, but we do have inversion of configuration. Okay. Now that also means that our methyl and our primary are the most reactive, where secondaries can react in the right solvent. So going over to our SN1s now, that means we have a stepwise. It forms the carbocation first, and then it forms the final product. Okay, that means that we only care about the concentration of the alkyl halide because we have to wait for the carbocation to form first. If we form a carbocation, we have to worry about carbocation rearrangements. Because our carbocation is trigonal planar, we worry about racemization, or a 50-50 mixture of attacking one side versus the other. And because tertiary and secondary carbocations are more stable, they are more reactive, and rarely do we see them in primary or alkyl halide or methyl halides.